Is that going to focus? Why is it not? Well, maybe it focused. Okay. So the first thing, we're going to see a lower bound that says that in general, in the comparison model, okay, reset this, start this again. You can't do better than n log n comparisons in general, okay? And there's a figure in the notes, yeah, so which is a decision tree. So suppose you have some algorithm A which works on comparisons. It's going to take n numbers, n things, and it's not allowed to look inside the things. All it's allowed to do is, we can assume the things are distinct. It's a set, so that the elements are distinct. We can just hold up two elements and say x and y, is x less than y, is x greater than y. Okay, x equals y doesn't happen because they're distinct. So in the notes, there's this cute little decision tree. Also in the textbook, there's a cute little decision tree saying, okay, here is, I drew a decision tree last night for if you're sorting 3 elements. Here is, you compare x1 and x2, and then if x1 is smaller than x2, then you compare x3 and x2 and x3, and so, okay. However, even if the algorithm is randomized, you can say, okay, fix its source of random bits to be something, and then we can analyze it. Now, imagine this decision tree. So how many leaves does this decision tree have? Well, it has to have at least one leaf for each possible ordering of these n elements, right? So it has to have, so the decision tree for algorithm A, sorting n elements, has at least n factorial leaves, right? Because at each leaf, it says, okay, this is the order, and there are n factorial possible orders. So it's binary, right? Because at each time you get a comparison, you get a yes or no answer. Is this smaller than this? Right? So it's a binary tree. A binary tree with n factorial leaves, at least n factorial leaves, has height omega log, so this is actually, okay, I don't even need the omega yet, at least log n factorial. Ooh, what's this? We know this. We saw this in the last lecture, one of the previous lectures. We know what that looks like because of Stirling's formula, right? Which it was the last lecture because I was saying, look, Stirling's formula includes big O notation, and this doesn't mean it's bad. Actually, in the lecture notes, I was having fun because I was saying, oh, and here I'm using omega, and it's a worst case, and it's O, and it's the best case. And actually, we'll get to that in just a minute. So, what is log n factorial by Stirling's formula? So this is, oh, I should do this no, we didn't actually see log n factorial. We saw ln n factorial. Which is ln n factorial over ln 2. Am I getting this? Yeah, right? So log n factorial equals 1 over log e, just a second. I can do this, but not while I'm standing in front of you. So wait, I have this as being 1 over, I have this as ln n log, yeah. Oh, right, so this should be ln 2. And then by Stilling's formula, it's n ln n minus n plus o. It doesn't, it only changes the constant factor anyway. Log n. And this is all omega n log n. Right? So, omega. Yay, omega. So, we know that the decision tree has some long path, okay? Right? Some leaf has to be deep. That means that, and in fact, that if we, even if it has multiple copies, if it has multiple leaves for the same ordering, which it shouldn't, then we can just consider the highest leaf for each one. There are still n factorial of them. That means one of them has to be deep. So there has to be some ordering where any leaf corresponding to that ordering has to be of depth at least omega, well, at least is omega. It has to be of depth omega n log n. That means that in the worst case, for any comparison-based algorithm, there is some permutation of the n elements for which it does omega n log n comparisons. Okay? Good. So we have a lower bound for comparison-based sorting. Where did the eraser go? Okay, that's, oh, here it is. Okay. So now, does that mean we always, excuse me. Does that mean we always need, if we're doing comparison-based sorting, we always need omega n log n? No, it doesn't. For example, now some algorithms maybe. For example, selection sort is always is always going to use about n squared. Now you've probably heard insertion sort. Most people know how to do insertion sort. If you take insertion sort, it also has a worst case that's n squared. That's like omega n squared. It's actually theta n squared. And you can see this because if you imagine taking insertion sort I'm not going to finish on time on 1, 2, 3, 4, up to n. What's it going to do? It's going to take the 1 and it's going to put it in a list. And then it's going to take 2 and it's going to compare 2 to 1 and then it's going to put it next. And then it's going to take 3 and it's going to compare it to 1 and 2 and it's going to put 3 next. And so when it does this, for the number I, it's going to do I minus 1 comparisons, right? And so you're going to get 0 plus 1 plus 2 plus 3 plus n minus 1. And this is theta n squared. But now, let's consider insertion sort if you give it the numbers n, n minus 1, n minus 2, n minus 3, 2, 1. Okay? So now what's it going to do? It's going to take n away. It's going to put n here. It's going to take n minus 1. It's going to compare it to n. And it's going to put n minus 1 here. And then take it away. It's going to take n minus 2 and compare it to n minus 1 and put n minus 2 in front of n minus 1. And then it's going to take n minus 3 and compare it to n minus 2 and put n minus 3 in front of n minus 2. So for each of these numbers, it's going to do one comparison. So then it's going to run in linear time. So actually, the insertion sort's worst case is when you give it a sorted list, and insertion sort's best case is when you give it a list that's backwards. And in its best case, it takes linear time. Okay, so best case, we generally don't care about best case because it's not that informative. We're more interested in things like average case. Well, worst case, we really like worst case. Average case is like, meh. Some people care about notions of pre-sortedness. So I have a friend, Jeremy, who he considered, for example, if the input can be broken up into a small number, can be partitioned to a small number of sorted subsequences, then you can sort it faster. This will actually come up late in some other, I'm going to use this later, several times actually. Maybe it's an exercise. Yes, probably it's an exercise. That would be cool. So now let's talk about my new algorithm, no sort. Okay. Well, okay, most stuff has a good best case. Except like selection sort, which has its worst case and its best case is always theta n squared. But usually it's usually for most algorithms there's some input for which it's pretty good. So that's not saying okay, merge sort. So let's talk about merge sort. So we've seen that we can actually, so it's not hard to do. So insertion sort, you can show that it's quadratic. Selection sort is quadratic. Let's see that merge sort is n log n in the worst case. Okay. So recall that for merge sort, what we do, we have a list of an array of numbers, and we have A1 to AN. So let's say S, because we used A for the algorithm. S1 to N, because later I was using S as a subarray. We choose, we divide it into S1 to floor of n over 2, and I'm not and S, say floor of n over 2 plus 1, and then we recursively sort these, and then we merge them. How do we merge them? I wrote the code in the lecture notes, so I was saying, assume that you take these two subarrays, you want to merge them. Conceptually, you append infinity to the end of either one of them, and then you just have three pointers I, J, K, and so it's like I equals 0, J equals 0, K equals 0, and then while so it's, you have S1 I not equal infinity, or S2 J not equal infinity. So remember, conceptually we've appended infinity at the end of either of these things. If S1I, there might be a mistake in this. I haven't actually tried it, but is less than S2J, then, so this is going to come up in the next lecture when we discuss some other stuff. Then S is the output, SK equals S1I, I plus plus, K plus plus, and then you say else SK equals S2J, J plus plus, K plus plus. So it's just saying and if and while. So it's just saying, okay, look at the two numbers and take the one that's smallest and put it in the output array. Okay. What's written inside while? Everything under while. Yeah, so the while is closed here. So this is if, else, and this is while. So how long does this take? 15 minutes. Yikes. Well, how long does the merging take? It takes linear time. Okay. Unless you mean the condition. So I'm just saying that as long as I haven't got to the end of both lists, S1i not equal to infinity or S2j not equal to infinity. There could be a bug in this. Okay, so the recurrence is going to be, I'm going to Tn, I'm going to sort two. Now this is why in the master theorem it's nice that it says, yeah, we ignore the floors and ceilings on n over b, right? Remember that from last time? We say we have two subproblems of size n over 2, and then it takes us linear time, like n time, to do the merge. And we look at that and we're like, oh, that's easy. That's the second case of the master theorem. That's when the splitting up and the subproblem shrinking is about balanced. So that means that the amount of work at each level of this recursion tree is about equal. So remember that said, then Tn is theta log base b, n to the log base b of a log n. Right? So this is just what is a to what is b to, so this is 1, so this is equal theta n log n. Okay, so merge sort is n log n. We know that recurrence Fn is big. Yeah, because this, yes. Because here, yeah, the f of, I got it, I said this in the lecture notes. N is, so f of n equals theta n to the log base b of a. This is just log base 2 of 2. So this is 1, so this is theta n. Yes. Thank you for reminding me about that. Okay, so we have 12 minutes for quick sort and quick select. Yay! This is not really enough time. So merge sort, n log n in the worst case, easy by the master theorem. So now, what about, have people seen quicksort? I assume you've seen merge sort. You know quicksort, right? Okay. So quicksort, what's the worst case for quicksort? So quicksort, usually you pseudo randomly pick a pivot, right? You have this, you have S 1 to n, and you pick a pivot, and you partition stuff into the numbers smaller than the pivot and the numbers bigger than the pivot. And so in the worst case, however the numbers are mixed up, you pick the smallest one or the biggest one. But say you pick the smallest one. You then partition, you spend linear time partitioning, and all you've got is this huge partition that has n minus 1 things in it, and this your pivot. And then if you're very unlucky, the next time you pick the smallest remaining element and you partition. So this means if you consider the recursion tree, it's degenerate. Okay, it just like stabs down, like you've got the trace is a degenerate tree, and it's very bad, and it's very deep. It's linear depth. And you're doing linear work at each level. So it's n squared in the worst case. Well, it's theta n squared in the worst case. Why do people use this? Why do we teach this? Because you have to be very unlucky for that to happen. So, how unlucky do you have to be? Well, let's imagine we have some S prime is S sorted. So we have S prime. Let's imagine it as this rectangle. Okay? And this is a quarter. This is the first n over, well, let's say that this point is n over 4, and this is 3n over 4. Okay? Now, let's suppose that I'm going to consider myself lucky if my pivot, now remember S prime is sorted, if my pivot is in like the middle half of S prime. We don't actually sort the things before we choose the pivot. Although, if we have time, I will mention something like that. Maybe we're probably not going to have time. But I'm going to conceptually, because I'm choosing it pseudo-randomly, so the chances of me ending up in the choosing an element from S that would belong in the middle half if the things were sorted is about half, right? And the chance of me choosing it at one end is also half. Okay? So I'm going to consider myself, it's a lucky pivot, it's a lucky choice of pivot if it's in the middle half, and it's an unlucky choice of pivot if it's at one of the ends. Okay? Now, let's consider, it doesn't actually make the algorithm run faster if I decide that I choose a pivot, and then I do the partition, and if I do the partition and the partitions are very uneven, so one of the partitions has more than 3/4, then I don't like that pivot. I take everything, merge it back together, and do it over and pick a new pivot. Okay? So if I choose somebody here, then neither of the partitions can be 3/4. Right? Right. So when if I choose a pivot from the middle half, then the biggest, the biggest it can be is like n over 3/4 of n minus 1. Okay, so there could be like off by 1 errors here, but I have to choose an unlucky pivot in order for the partition to be very skewed. And the problem with that, the probability of that happening, if I choose it pseudo-randomly correctly, is at most a half. So okay, if I'm going to choose a pivot, I'm going to do the partition, and if I've got a good partition, then I'm just going to keep going. And if I've got a bad partition, one of the pieces is more than 3/4, I'm going to choose a new pivot and repartition. Okay? So to do this partition takes me linear time. So how much time do we expect to take before we get a good pivot? Well, the chances of the chance of me choosing a good pivot on the first try. So what are the chances of me using one try, choosing one pivot, and it's a lucky pivot, and I just keep going? Well, that's the chances of one try are what's the expected number of tries? I'm going to cut one step out. So the probability is 1/2 that I use one try. I choose one pivot. And then the probability is it's 1/4, right? Oh, so because why is it 1/2? The probability is 1/2 that I just choose a good pivot. To choose, if I wanted to have exactly 2 tries, it means I had to choose a bad pivot the first time, and then I choose a good pivot. So that's a probability 1/2 and a probability 1/2. So probability 1/4. I actually went in a bit more detail in the lecture notes. So that's a quarter times 2, plus an eighth times 3, plus a 16th times 4, plus blah, blah, blah. So this is sum over I greater than or equal to 1 of I over 2 to the I. How? Okay, we're going to get 4. Then I'm going to let this thing keep running, and then it's just going to lose the end of the... And maybe I'm going to have to edit these videos. I have 5 minutes left. 4 minutes left. Okay. So I'm going to do this.